Okay, so this week we're going to be dealing with Experiment 7, which is a dry lab. You're going to be coming to the laboratory, working some problems on paper about how to interpret NMR spectra. And in this lecture, we're going to talk a little bit about the theory of NMR in general, and we'll also talk about the proton NMR. So there are two types of NMR. There's proton NMR and carbon NMR. You'll be learning about both of those in this laboratory, but we're going to break up the video series into Part A and Part B. Part A, again, we're going to be dealing with only the theory of NMR in general and the proton NMR, and then when we return in Part B, you'll be learning about carbon NMR, which is actually a lot more simple to interpret than is proton, and then we will talk about a problem-solving strategy for what you're going to be doing in lab. So this is not a short video series. Make sure you allow yourself plenty of time to watch this prior to coming to lab. NMR stands for nuclear magnetic resonance, and it is related to probably what everybody knows about is MRI, magnetic resonance imaging, which is a medical technique, but they work on the same principle. And arguably, NMR is the most important spectroscopic technique available to chemists. It gives us a wealth of information, and if you asked a chemist what one instrument must you have to do any type of research or work, they would arguably say an NMR. It allows us to identify unknown organic molecules without the need for standards. You may recall back to when we were doing GC and TLC, you were able to determine what you had using those techniques, but only if you had standard compounds to which to compare your unknowns to. However, that's not necessary in NMR. NMR gives you enough information to actually solve your problem quite easily. Let's look at a model for an atom. And again, NMR standing for nuclear magnetic resonance. What we're talking about is the nucleus. And if you think of the nucleus as just a sphere, it's a sphere that is positively charged. And I've simply drawn it with a single positive in there, representing, of course, the proton. But fortunately for us, the proton has a positively charged nucleus, but that nucleus is spinning. And I want to depict spinning using a curved arrow around the sphere. And so it's spinning kind of like a top. And anytime you have a charge that is moving, we generate an electromagnet. So you can think of hydrogen atoms, basically, or the protons, if you will, as small electromagnets. And when this spins and generates its magnetic moment, we're going to represent the magnetic moment as a vector. And I've just arbitrarily drawn it going up. We could have just as easily arbitrarily drawn it going down. It doesn't matter. Okay, so this is our vector showing our magnetic moment. Now, if we have an organic molecule, these magnetic vectors are going to be randomly aligned if they're not placed in a magnetic field. So what we have in this box is just a series of protons. All I'm showing them by is their magnetic vectors. You can see that it's randomly oriented. There's 9 of them in this box. And so this is in the absence of a magnetic field. However, if we took that box of magnets, if you will, and placed them into a strong magnetic field, it can only have 2 possible orientations. So if we place it into a strong magnetic field, I'm going to draw the strong magnetic field here. We call that B0. Okay, so B0 is just a strong external magnetic field. Now, these so-called spins or magnets can either align with the external magnetic field or they can align against the magnetic field. And one way to think about this is the north and south poles of a magnet. If you have a very strong magnet and you throw in a box of small magnets, they can either align with that strong magnetic field or against it. And it turns out that for the proton, you're going to have a slight population of most of them aligning with and fewer of them going against the strong magnetic field. Okay? This is what the NMR spectrometer supplies. So you've got a picture of the NMR spectrometer that we actually use in our department in your laboratory manual, and it looks like a big can. It's really just a big superconducting magnet that supplies B0. So if we look at a graph of energy on the y-axis, so energy is increasing in this direction, and we look at B0 here, increasing B0 going to the right, I've got a couple of things listed here. And so what we have is the two possible states. So at lower B0, we have the alpha state and the beta state. The alpha state being the one that is aligned with the external magnetic field. It's the lower energy. And we have one here known as the beta state, which is aligned against. In this particular situation, these states are said to be quantized. It's either alpha or it's beta. There's nothing in between. So either our spins are aligned with the magnetic field or against. They're not randomly oriented anymore. So it's said to be a quantized state. This energy difference here can be measured very easily. And so that's what the NMR spectrometer actually does. Basically what we do in an NMR spectrometer is we take this alpha state, we put energy into it, it gets absorbed, and it promotes it to the beta state. Again, we had more spins in the alpha state than the beta state, and so we can actually populate the beta state by moving some of those from the alpha state to the beta state. And in doing so, we can actually measure the absorption of energy. When you have a very small B0, this gap is very small. I've kind of exaggerated it here for ease of viewing, but it's actually quite small at very small external magnetic field strengths. However, if you go to higher magnetic field strengths where B0 is actually quite large, the energy gap between the alpha and the beta state gets larger and it becomes easier to detect. And so that's why we use superconducting magnets in our NMRs these days to get this large gap in the two states so that we can easily detect the alpha and the beta state, and we get better sensitivity that way. So that's the physics of how an NMR spectrometer works. Seems pretty simple. We just start off here and we populate up to the beta state and measure the energy that's absorbed. Okay? But when we go to Proton NMR, let's talk a little bit about some of the practical things. So we call this Proton NMR. All we're looking at is hydrogens. Okay, so we're going to be able to detect the hydrogens in our molecule. Unfortunately for us, most organic molecules, actually all organic molecules, right, have to have some hydrogen, and so we're going to be able to see those very well. Just as a quick side, it turns out that when you go to the doctor or to the hospital and you get an MRI, they're doing basically a proton NMR experiment on you. We're mostly water, and water has a lot of protons in it, obviously two protons for every oxygen, right? So there's a lot of hydrogen around that the MRI can use to make its image, and it does this using basically what is NMR technology. But the types of information that we're going to get from an NMR spectrum include the chemical shift, and this is represented as parts per million, or ppm, and we frequently abbreviate that by just using a delta sign. Okay, so when we're talking about ppm or delta, we're really talking about the chemical shift of a particular signal. And you'll see what I mean by that in just a minute. We also get information on the splitting pattern of the signal, how the signal is split. So we get a chemical shift, but that can be split into a pattern that we can actually interpret that tells us something. And that follows what's known as the N+1 rule, which we'll talk about in more detail here in just a minute. And we can also get information known as the integral. And just like integration, when you were talking about GC, this tells us something about the number of protons. So this tells us the relative number of protons that give rise to that chemical shift. So we can look at a chemical shift that tells us something about the molecule. We can look at the splitting pattern using the N+1 rule, which we'll talk about in a second, which tells us a little bit more information. And we can look at the integral, which will tell us how many protons were giving rise to that signal. So that's a lot of information in this very simple experiment. So let's look at an example, and we're going to apply these different pieces of information